All right, so now that we know how to take these cute little messages, so these little 4-bit phrases, and convert them into their respective code words, what I want to do now is begin morphing it into this process of, okay, how do we actually use this crazy little construction to, in fact, detect and correct some of these little errors? The key here is actually going to be in the structure of this little G. So as I mentioned before, it essentially is of the form some identity matrix out in front, followed by this crazy little essentially shadow of an identity matrix on the back end, which I'm going to refer to this thing as a Q. So what's going to emerge next is we're going to have this process that we're going to take that little Q and we're going to begin constructing a new little matrix with it. We're going to call this matrix H, and then we're going to use this H to compute something that's referred to as a syndrome. If the syndrome emerges as all zeros, we know in fact that we're going to have no error actually detected. If the syndrome kicks out something that's non-zero, that's actually going to shed some light into where our error actually occurs. So the way that this is going to be constructed is the following. We start with our little matrix G, which is again an identity followed by some crazy little Q. What we're going to do is we're going to build a new matrix called H, which is going to be the transpose of that matrix Q. So the transpose is where we swap the rows and columns, and then we're going to shove in a new identity matrix at the end of that thing. So that's going to become this new little parity check matrix H. Then what we're going to do is we're going to take the transpose of that thing, and that's going to be the bit that we actually multiply by these received code words. So we're going to be starting with things like this. We're going to be multiplying that by this H transpose. If that emerges as a 0, we're in good shape, and that there was no error that actually emerged. If it's non-zero, some really, really cute things are actually going to happen. So let's go and actually build up the respective little H for this 7-4 code. So here is my G. So this little part in the back end is my Q. So it again is this kind of almost shadow of an identity matrix in that there's zeros along that diagonal. It's not square in that there are only 3 columns and 4 rows. So when I take the transpose of it, what's going to happen is that the rows and the columns are going to switch. So instead of having 3 columns and 4 rows, it's now going to have 4 columns and 3 rows. So I tried to kind of showcase how this little swapping is going to happen. So if you look at this third row of Q, it is of the form 1, 1, 0, which then becomes the third column of Q transpose. So that little 1 that is essentially orange then becomes the top bit, and then it's going to have the rest of it going down. So you kind of think that you have this little diagonal here, and then you're going to spin this thing along that. So we're swapping those rows and columns. So that becomes my Q transpose. What I'm going to then do is I'm going to take that and then I'm going to shove a new identity matrix at the end of it. And that's then going to form this little matrix H. And then what I can do at the end of it is I can compute H transpose again by twisting that thing. So what that's going to look like is then it's going to look like this crazy little matrix right here. So here's where I'm doing this all in one step, basically, is I have my original G, I'm going to build my H, and then I'm going to take the H transpose. So what I do next is I'm going to take those little code words that we are accepting. So we knew that we built up this little code word of 1100110. That one has no errors because it was specifically constructed not to have any problems. So if I take that little code word and multiply it by this H transpose, I'm going to compute what's referred to as the syndrome of that little code word C. I do the same kind of crazy little twisty multiplication, and it's going to nicely emerge as all zeros. So I'll run through maybe, let's say, the first column just so we're all kind of on the same page of how this arithmetic is going to work. So let's do that crazily up here. So I'm going to get a 1 and a 0 for the first things, plus a 1 and a 1 for the second things, plus a 0 and a 1 for the third bits, and then plus a 0 and a 1 for the fourth bits, plus a 1 and a 1 for the fifth bit, and then it's going to be a 1 and a 0 for those, and then ultimately a 0 and a 0. So what is that all going to emerge as? A 0 plus a 1 plus a 0 plus a 0 plus a 1 plus a 0 plus a 0, which is a 2, which if I reduce modulo 2, is in fact going to be a 0. So that's where that first little 0 is going to emerge from. And if you go through the whole process on that, all three of those things are going to 0 out, which is great, which is to say that this little code word in fact has no errors. And because I know that it's a 7-4 code, my original little message should have in fact then been the 1100. So everything is awesome. No issues, no problems, no flips of bits. Everything is as I would expect. So that's the idea, is that we're going to compute this little syndrome. If the syndrome zeroes out, everything is great. If the syndrome is anything but zeros, I know that an error is going to emerge. And moreover, that's actually going to tell us where the error occurs. And it's this cute, adorable process that is great. And you're gonna love it because it's really neat and it's a lot of fun. So here we're gonna take that code word that was originally 1100110, and I'm going to switch one bit. So let's say in transmission, that second to last bit, instead of being the 1 that it was supposed to, we're gonna change it to a 0. So we definitely see, well, we know that there's an error, but now we want to see how this little machine is actually going to recognize that error. So just like before, what I'm going to do is I'm going to take that little code word and I'm going to multiply it by this H transpose. So I'm going to compute the syndrome of this code word, which I'm viewing as C1. So if you do this crazy twisty multiplication, what's going to emerge is you're going to see that a non-zero thing ends up on that right-hand side. So right from there, you're going to have in this little decoder process, there's an error. Definitely an error because this is not zeroed out. So then you're like, cool, great, I have an error. Where did it emerge at? And this is the adorable part. This is the part that it's really, really cute, is that syndrome, that 010, is an element of that H transpose. It's actually the 6th row of that thing. And the error emerged in the 6th cell of that bit. And that's not a coincidence at all. So we know that the syndrome is going to emerge, and then you compute where in that little matrix H transpose does that syndrome live, which is actually really easy to do in code because you're going to view this big matrix as a list of lists. So you're going to ask, what index does the 010 happen to live on? And that's going to tell you then where the error actually emerged from. So then to fix it, you're just going to switch whatever bit you happen to have into a 1, and everything is great. So we could nicely correct this thing, and it's awesome and great. It takes very little effort. It's just a simple little bit of multiplication, and then everything is gravy after that. So it's cute and awesome. So if we wanted to do another example, we could do this one. So we have the code word incorrectly viewed as 1110, 110. So we know it's supposed to have a 0 in that 3rd cell. So we have an error there, but let's say we didn't know this part. This part was all unknown to us. So we're just receiving that code word. Well, what you do is you again compute this little syndrome. So you're going to take that code word C2, you're going to multiply it by that crazy big old matrix, and voila, it's going to emerge as a non-zero thing. So immediately you have the alarm saying, hey, there's definitely an error happening here. You can see that it is the 3rd entry in that matrix, which tells me that my error is in the 3rd cell. So it's adorable. I love it. It's great. Students have a lot of fun with it because it's this weird process that feels like a little bit of magic. And the magic is actually all embedded into the very specific construction of this matrix G that we had at the very, very beginning. So there's a little bit of theory that we're going to jump back into after we chat about the crypto systems we can build up with these codes. But there's a very special connection between the 7 and the 4, i.e. this redundancy of 3, and then how we're actually going to build up this second portion of this matrix. So if right now we're going to view it as the little shiny toy that does in fact work, and it builds up this brilliant theory that's going to allow us to correct some of these singleton errors, and then we're going to take that information and then pull it back and actually use it to showcase all of the additional wonderful goodies that we want to in fact see.